dear learners. Welcome to the course on Fundamental of Electronic Engineering. Today, we are going to discuss about the introduction and the basic concepts of electronic engineering. I am Dr. Onika Parmar and I welcome you in this course. So, in this lecture, we are going to discuss about the electric field, electric potential, electric current, Ohm's law, resistance and capacitance. So, let's start with electric field. Electric field is a region of space around a charge or a system of charges within which other charged particles experience electrostatic force. Theoretically, electric field extends up to infinity, but practically it is limited to a certain distance. It is also called as electric field strength or electric field intensity. The test charge is thought to be vanishingly small because its presence should not change the configuration of charges, thus the electric field to be measured. The electric field strength at a point in an electric field is the electrostatic force per unit positive charge on a vanishingly small positive test charge placed at that point. The electrostatic force per unit positive charge acting on a vanishingly small positive test charge placed at a point in an electric field is defined as electric field strength. Here in this figure, you can see that there is a source charge Q. Q0 is the test charge, F is the force and E is the electric field. We can say electric field E is equals to force divided by the test charge. It is also equals to or E is also equals to 1 by 4 pi epsilon naught Q upon R square into R. So, there are few points to be noted. Since Q0 is taken positive, the direction of electric field E is along the direction of electrostatic force. As Q0 is assumed to be positive, the direction of the electric field E is parallel to the direction of electrostatic force. The electrostatic force on a negatively charged particle will be directed in the opposite direction as of the electric field. Electric field is a vector quantity whose magnitude and directions are uniquely determined at every point in the field. The magnitude and directions of the electric field are very unique. The SI unit for electric field is Newton per Coulomb. So, there are few properties of electric field lines which should be discussed. So, you can see in the figure there is an electric E and there is a charge of 1 coulomb. The electric field line of forces are imaginary line. These lines are fictitious. A unit positive charge placed in an electric field tend to follow the path along the field lines and if it is free to do so. The electric field lines emanate from the positive charge and terminate on a negative charge. That is, the electric field line starts from a positive charge and ends to the negative charge. The tangent to an electric field line at any point gives the direction of the electric field at that point. Suppose we want to determine the direction of the electric field, then we can take the tangent from there and the direction of the tangent will give the direction of the electric field. So, continuing about the properties of the electric field, two electric fields can never cross each other. If they do so, or let's suppose two electric fields cross each other, then if we draw the tangents from those electric field, we will get one tangent at some direction and another tangent at some another direction, which is not possible in the case of electric field. The electric field tangent is or the tangent from the electric field is the equivalent of these two tangents. So, two electric fields can never intersect each other, they will run parallel to each other only. Further, electric field being a vector quantity, there can be only one resultant field at a given point, represented by one tangent and a given point for the given lines of forces. The next property is electric line of forces can pass through an insulator. An insulator can permit the passage of electric field lines. So, let's discuss about the behavior of conductor if it is placed in the electric field. So, the first point is the net charge inside a conductor is 0. So, if we place a conductor in an electric field, what will happen? The charges are separated temporarily. The positive charge will align to some direction and the negative charge will align to opposite direction. So, the net charge inside a conductor is 0. Suppose we place a conductor in an electric field. So, what will happen? The positive charge will move to a certain direction and the negative charge will move to a certain direction. So, overall, the net charge will be 0. The charges are temporarily separated. The total charge of the system is 0. Charge always resides on the surface of a conductor. The surface of a conductor is where charge is always found. Electric potential is constant for the entire conductor, or for the entire conductor, the electric potential is fixed. Since electric field E is equals to 0 inside the conductor, therefore dV is 0, that is V will be constant. Electric potential at a point in the electric field is defined as the work done in moving a unit positive charge from infinity to that point against the electric force irrespective of the path followed. Electric potential is the work required to move a unit positive charge from infinity to a specific point in the electric field against the electrostatic force regardless of the route taken. Electric potential is a physical quantity which determines the flow of charges from one body to another body. A physical property called electric potential controls how the charges will move from one body to another. It is a physical quantity that determines the degree of electrification of a body. The electric potential V at any point in this space is defined as the electric potential energy U per unit charge Q at that point. It is expressed by the equation shown below. The SI unit for this is Newton meter per coulomb, or we can say joule per coulomb. A point's electric potential is equal to 1 volt if 1 joule of work is expended to move 1 coulomb of charge there from infinity in an electric field. Now, we are going to discuss about electric current. So, electric current is defined as the charge flowing through any section of the conductor per second. Electric current can also be defined as rate of flow of electric charges through a conductor. Its expression is given as I is equals to Q by T or dQ by dt. So, I is equals to Q by T if the rate of the flow of current is steady, and I is equals to dQ by dt if the rate of flow of current varies with time, where I is the electric current measured in amperes, Q is the charges passing through the cross section of the conductor during the time T. This is measured in coulomb. T is the time taken for the charges to pass through the cross section. So, basically, conventional current is the current whose direction is along the direction of the motion of positive charge under the action of electric field. Conventional current is the flow of current that follows the path taken by the positive charge as they move under the influence of electric field. So, there is steady state current. Steady state current does not vary with time. Here we can see the current and the time graph, and we can see the steady state current moves in a straight line, while the varying current whose magnitude varies with time, or we can say the varying current are those current whose magnitude varies with time. We can see there are various movements in the curve which is purple in color or green in color, while we can see that the blue one is straight. So the steady state current flows in a straight line, the magnitude never changes, while in the varying current the magnitude varies with time. We can see a sinusoidal waveform there. Further moving towards Ohm's law. So, the electric current flowing through a conductor is directly proportional to the potential difference across the two ends of the conductor when the physical conditions such as temperature, mechanical strain or something else remains the same. Ohm's law is a fundamental principle in electric circuit that describes the relationship between voltage, current and resistance in a conductor. It states that the current passing through a conductor is directly proportional to the voltage applied across it and inversely proportional to the resistance of the conductor. Mathematically, Ohm's law is expressed as V is equals to IR. Overall, Ohm's law says that V is directly proportional to I, and to remove the proportionality constant, we use resistance R. So here we can see there is a conductor in the circuit across which a potential is applied, and when we apply a potential across that conductor, the current I flows in the circuit. A current always flow in a closed loop condition only. So here we can see it forms a closed loop. The voltage is provided at the conductor whose resistance is R and the current flows across it. And if we draw the VI characteristics here, we can see the resistance increases linearly. Here we can see the purple line in the curve shows that the resistance is increasing in a linear pattern. So, in simpler terms, Ohm's law tells us that if the voltage across a conductor increases while the resistance remains constant, the current flowing through the conductor will also increase. So, R is equals to V by I. The resistance of the conductor is the opposition offered by the conductor to the flow of current, where so we can define resistance as the relationship between voltage and current in an electric circuit as described by the Ohm's law, and the equation for resistance is equals to V by I. Here R is equals to resistance and it is measured in ohms. V is the voltage which is measured in volts V, and the current is measured in coulombs, or the current is measured in amperes, where R is the resistance of the element and it is measured in ohms. The symbol for it is shown here. The voltage is measured in volts and the current is measured in amperes. This equation signifies that the resistance of a conductor or the component is equals to the ratio of the voltage applied across it to the current flowing through it. The resistance of a conductor can be mathematically expressed in terms of the physical quantities, namely the length and the cross section of the conductor, as well as a very important term there is resistivity of the material. Resistivity is a material property. Here resistance R is equals to rho L by A, where R is the resistance of the conductor, rho is the resistivity of the material, and it is given as ohm meter, or the unit is ohm meter. The length of the conductor is given in meters and the cross section area A is given as meter square. In this equation, resistivity is a material property that describes how strongly a material opposes the flow of electric current. It varies depending upon the type of material and is constant for a given material at a specific temperature. Therefore, a longer conductor, a material with high resistivity, or a smaller cross-section area will result in high resistance and it will restrict the flow of current. There are various types of resistor. One of them is a carbon resistor. The carbon resistors are color coded. The color code of a carbon composition resistor, also known as carbon film resistor, and it is used to indicate their resistance value through the tolerance level. The color code consists of 4 to 5 color bands that are painted on the resistance body. Each color band represents a specific value or multiplier. The color code of carbon resistors are as follows. The first band represents the first significant bit of the resistant value. The second band represents the second significant bit of the resistance value. The third band indicates the multiplier or number of zero to be added after significant digits to get the final resistance value. And the fourth band is optional. Some resistors may have a fourth band which indicates the tolerance level or the allowable deviation from the standard value or the stated value. If there is no fourth band, it indicates a standard tolerance level. The color code are as follows. Black corresponds to number 0, brown corresponds to 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, grey 8 and white 9. And the colors golden, silver and no color represents 5%, 10% and 20% tolerance respectively. Here are the few examples. If we have brown, violet and black, then we will have with a golden band. Then we will have 17 ohm of resistance with plus minus tolerance of 5%. If we have green, red and blue along with the silver, then we will have 52 into 10 to power of 6 plus minus 10% of the tolerance, and the unit will be ohm. Suppose we have black, violet and brown. In that case, it will be 17 and the tolerance will be of 20%. Here we can see there is no band or there is no color at the last band. In the first two there was golden and silver. In this one there is no color. So if there is no color, then it will show the 20% of the tolerance. The value or the unit will be in ohms. Now the resistance can be made in the parallel and the series combination. Parallel and series combination are the two common ways for connecting the electrical components in a circuit. So let's discuss about the series combination. In a series combination or in a series circuit, components are connected end to end, creating a single path for the current to flow. The same current passes through each component in the series. The total resistance in the series circuit is the sum of the individual resistance as shown below. The voltage component across the series will add up and will get a total voltage V, or we can say that in a series combination voltage varies while the current remain the same. So let's suppose the three resistors R1, R2 and R3 are connected in series to each other. Then the total resistance will be given as R1 plus R2 plus R3, and the overall equivalent resistance R will be greater than R1 and R2 or R3. It will greater than all of them. So parallel combination. In the parallel combination, the components are connected side by side. Here the current is divided into three parts. It will go to R1, then R2 and R3. So the voltage across R1, R2 and R3 will remain the same, and the current will vary in the parallel combination, and the equivalent resistance is given as 1 by R. Here R is the equivalent resistance and it is given as 1 by R is equals to 1 by R1 plus 1 by R2 plus 1 by R3. The equivalent resistance R will be smallest in all the case. That is, from all the three resistance, the equivalent resistance R will be the smallest one. Now, another important topic is capacitance. Electrical capacitance is a fundamental property in an electric circuit. that describes the element's ability to store the electric charges. It is denoted by the symbol C and it is measured in farads. Capacitance is the result of the presence of two conductive plates or a surface separated by a insulating material called a dielectric. When the voltage is applied across the capacitance or the capacitor, positive and negative charge accumulate on the respective plates, creating an electric field between them, and the magnitude of the charge stored on the plate is directly proportional to the applied voltage. C is equals to Q by V. Here Q is the electronic charge, C is the capacitor and V is the voltage. Capacitance is measured in farads. Capacitance of a parallel plate capacitor. The capacitance C of a parallel plate capacitor is determined by the geometry of the capacitor, specifically the area of the plate. The distance between them is represented as d. The capacitance is a measure of the capacitor's ability to store charge at a given voltage applied across the plates. The equations for the capacitance of a parallel plate capacitance is equals to, or capacitance C is equal to epsilon A by D. Here A is the area of the plate and D is the distance between them, and epsilon naught is the permittivity of the free space. The equation shows that the capacitance is directly proportional to the area of the plates and it is inversely proportional to the separation of the distance between the plates. It means that a larger area and the smaller distance between the plates result in the higher capacitance. Now, the capacitance, if they are connected in series, or we can say they are connected back to back. In that case, the equivalent capacitance C out will be the reciprocal of the capacitance, that is 1 by C out will be equals to 1 by C1 plus 1 by C2 and so on. Now, if the capacitors are connected in parallel, in the parallel condition, the equivalent capacitance C out is given as C1 plus C2 and C3. So, here we can say the total capacitance or the equivalent capacitance will be greater than the 3 capacitance. So, keep this in mind. In the case of the resistance, if they are connected in parallel, then 1 by R will be equals to 1 by R1 plus 1 by R2. While if the capacitance are connected in parallel, the equivalent capacitance will be equals to C1 plus C2 and so on. So, the condition for the resistance and capacitance are opposite to each other. So, today we have discussed about electric field, electric potential, electric current, Ohm's law, resistance and capacitance. These forms the basics which we should understand before moving forward towards the electronic portion. So, thank you for attending this lecture. Have a nice day.